So let me start with a disclaimer. A lot of projects in this summer school are related to streams in the halo of Milky Way and other galaxies that originate from disrupted globular clusters or satellites, but this stream is a different kind of object. And to understand, to get the idea of what is this Pisces Eridanus stream, let's look at the results of the study of Kunkel and Covey from 2019. So they used machine learning algorithms to search for clusters and coherent groups in Gaia DR2 data in the vicinity of Sun. And they found a lot of clusters and comoving groups, but some of them, almost half of this cluster, had this string-like, very long and very thin shape, spanning up to 200 parsecs. And you can see them on this screenshot from beautiful 3D animation in Marina Kunkel website. What is also interesting about these string-like structures, that's their lack of central cluster or central overdensity. And that implies that their filamentary structure might be primordial, which raises a question: could stars form in filaments? And to answer this question, we started our investigation of one particular object, Pisces Eridanus stellar stream, which was discovered by Mengest in 2019 and was their first object of this kind. So let's look at the properties of this stellar stream. It's very large, again, vertically confined with a vertical scale of only 50 parsecs. It is also kinematically cold, with a velocity dispersion of 1.3 kilometers per second. It also very chemically homogeneous, and it is relatively young, with a chemical and gyrochronological age of 120 megayears. So we want to know what was the shape of this stellar stream at the moment of formation. And for open clusters, we assume that they were born as the very tight spheres and then dissolved during their evolution and gets less dense. So we can start with the assumption that stream has maximum density at the burst time. And then we can take our observed stars at the present day, integrate backward, and explore the evolution of the shape of the stream and of the density of the stream. And to integrate backwards, we need several ingredients. So we need this external galactic potential. We used Milky Way potential plus bar potential. We also need to include self-gravity for these members of the stream. And we need to set up initial conditions. So for initial conditions, we first took the 255 stars from Mengest catalog, cross-matched with Gaia DR3 data. Then we fitted one component Gaussian mixture model to this 6D phase space coordinates with the use of extreme deconvolution algorithm. And then we could sample from this model as many stars as we needed. And here on these projections, you can see the comparison of spatial distribution of our XDGM generated sample with lighter blue dots and stars from real data from Mengest catalog in navy dots. And also we set the masses for these stars, for these generated stars. We drawn masses from group IMF with the use of Adam Ginsburg package, which is also called IMF. And the total mass of the cluster was set to 2,000 solar masses, corresponding to the extrapolation of initial mass function observed at present day from Mengest paper. We randomly distributed these masses along the stream. And body simulation was performed using Gadget 4 code with direct summation. We integrated our stream for 160 megayears. We tried different soft-inline lengths and decided on this one of 0.1 parsec. And the typical time step of integration was 1,000 years. You can see the orbit of the stream here. The orbit is almost circular and close to galactic plane. So my first assumption was that at the moment of formation, the stream has its maximum density. That means that we need to measure its density somehow. We used 3 different density estimators, and turned out that all of them gave the same results. But these are our metrics. So one of them was number of particles per convex Hall volume, where convex Hall is the smallest convex set that contains all the particles in the stream. Another one was density of the best fitting Gaussian ellipsoid, defined with this formula. And the third metric was kernel density estimator with Yepaneshnikov kernel and bandwidth of 0.02, which corresponds to 20 parsecs. So before going into the result of integration for the stream, it would be interesting first to consider the effect of uncertainties. And for this, we can look at the experiment that was proposed and kindly performed by Adrian. So the idea was to take the Gaussian sphere and integrate it first forward in time to see what's happening with the density. And we can see that at the moment of formation at time 0, the Gaussian sphere has its maximum density, and then it gets less dense. Then we can take this phase space coordinates at the end of integration at 250 megayears as initial conditions for backward integration, and see if we can spot the burst time as a moment of maximum density. And we can see that for the ideal case, without any observational errors, the burst time matches with the time of maximum density. However, if we will add some observational uncertainties on this 6D phase space coordinates at 250 megayears, we will notice that the moment of peak density is now shifted from the real burst time towards lower values. And if we will continue to increase the uncertainties, then at some point we won't be able to find the burst time anymore, because the moment of maximum density would match the beginning of integration. Looks like a bad news for us. However, if we will resample our observed cluster with XDGMM algorithm, then it will bring back the moment of maximum density towards burst time. And that means that our generated initial conditions with XDGMM algorithm might give some good results. I also said that we need to explore the shape of the cluster. And for this, we used ratios of variances explained by component of principal component analysis. So for the distribution, we can perform the BCA and then get ratios of these variances. They would correspond to axis of the triaxial ellipsoid. This was also called the sourcing head diagram in one of my weekly shares, and I'll later show why it is sourcing head. So let me show how it works for simple distributions. So the spheroidal distribution has both ratios close to 1 and falls into the top right corner of this plane. Then if we will start to squeeze the spheroidal distribution, it will move to the lower right corner of the diagram, where we can see this pancake-like distribution. And a blade spheroidal cigar-like shape has both ratios close to 0 and falls into the lower left corner of the diagram. So with these instruments in hands, we can analyze our results for our stream backward integration. So let's look at the density. Density doesn't look nice. We can see that the maximum density of the stream is now, and we also can find the second peak, which is at 40 megayears and is very inconsistent with the chemical and Gyre age of 120 megayears. But this might be related to uncertainties, as we have seen from Adrian experiments, and it requires some future investigation. Now let's look at the shape of the stream. So the shape of the stream looked like a sourcing head at some point, but now it's sourcing head under pressure. And what we can see from here that stream always evolved between prolate and the blade ellipsoid. and it never had a spheroidal shape. And these two projections show different views of evolution of the stream with color matching the color on the color bar. But to be sure that stream evolution is very different from the evolution of spheroidal distribution, we can compare this with Plummer sphere. So we used a Plummer sphere with this mass equal to mass of the stream and the range of different radii scale. We can see that Plummer sphere starts in the spheroidal part of head diagram and evolves differently from the stream. However, they are very close very close to each other at the end of integration. But if we look at their distribution, at the spatial distribution at the end of integration, we would see that they have very different structure. And this elongated shape of the Plummer sphere is provided by these very sparse arms. But the structure itself is different from the stream because it has a very dense core in the center, which we don't see in the stream. So one thing that we can do here is to clip the Plummer sphere and to compute the shape for the enclosed mass equal to 85% of total mass. And now we have very different evolution of stream and Plummer sphere. Plummer sphere always stays in the spheroidal part of head diagram, head plane, and stream evolves somewhere between prolate and ablate ellipsoid. That means that evolution of the stream is inconsistent with the evolution of Plummer sphere. And that implies that filamentary structure of the stream should be primordial. And if we'll get back to our question from one of the first slides, could stars actually form in filaments? The answer would be yes, they could. So this is a summary of what have been done in past 5 weeks. I performed a set of simulations of evolution of Pisces-Eridanus stream backward in time. We also developed the ways to measure the density of the stream and describe the shape of the stream as a function of time. We compared it to Plummer sphere integrated forward in time and found that Plummer sphere shows very different shape during the whole time interval of integration, indicating that filamentary structure of the Pisces-Eridanus stream should be primordial. And there's still a lot of work to do. So we can compare our stream with open clusters, for example, with Pleiades that have the similar age, and we already started to work in this direction. It would be very interesting to further investigate the effect of uncertainties on the density and on the shape of the stream, and investigate more this discrepancy between dynamical and chemical or chronological age. We also should try other ways of initializing initial conditions. For example, we can try minimalizing flow with deconvolution, and we already tried to do something in this field. And also, it would be very exciting to repeat this analysis for other streams from Hankel and Covey catalog. And that's it. And yeah, I have another minute to say thanks to my amazing mentors, Keith and Helmer, and to Adrian for discussions and experiments. And also I want to thank all organizers, mentors, and especially my fellow students in the school, because you made this time really amazing and unforgettable. Thank you.
Thank you. That was a great talk. You assumed a particular potential when you were doing these backward integrations. Have you looked to see what the effect of different potentials is on the density and on the shape?
We started with integration in just Milky Way potential without a bar, and just then we added the bar and haven't seen a lot of difference.
Cool. I just had a question on the PCA diagram. It looks like it kind of comes back around to initial conditions, and I was just wondering
This one?
Yeah, like it starts and ends in the same place, which seems interesting, but I don't know if you think it's just random or.
Yes, it's so. I think that we're not interested in the part of the diagram which is later than the maximum density. So at maximum density, if it's the burst formation, then the integration is reversible, and it doesn't matter if you integrate forward or backward. So yes, it starts as a stream, then it gets to the pancake-like shape, and then it became a stream again.
Okay. Hi, Anna. Very good talk. So I have one question about the density plot that you showed, that it seems like it's not increasing with time as you would expect.
Mm-hmm.
So, and you said that may be due to uncertainties in the initial conditions. So do you have like an idea of what kind of uncertainties you need for the density to go up rather than?
No, I don't have. I haven't looked at this direction very.
Okay.
Yes. So maybe we can like try different experiments and set different uncertainties at different initial conditions, and see how it will change this density evolution. And also, if the GMM assumes like Gaussianity of these initial conditions, maybe initializing them with other algorithms will change the density evolution.
Okay, thank you.
On Kunkel and Covey. So do you understand where I mean, it's a very interesting result that things are filamentary. Could that be driven by their selection effect of how they find streams? That they find things that are filamentary like, that's easier for the algorithm to find?
So they found a lot of structure. I just showed only the string-like clusters, but they also have not string-like groups too.
Good.
I was curious about the point where you said that if you resampled the stream using the XD, whatever it is, algorithm, Extreme D, then you got a better result when you did the test.
Yes.
Do you have an intuition as to why?
So this extreme deconvolution algorithm deconvolve the errors and uncertainties back. So it's related to.
I see. Can I ask?
Yeah. So when you talk about integrating back in time, so may I ask what time integrator are you using to integrate the system back in time?
Can you repeat again, please?
So what I wanted to ask is when you talk about integrating a system back in time, so normally when we integrate forward in time, we use like Wangakusa or something else. When you integrate back in time, which scheme are you using when you do that?
I'm not sure that I understood the question completely, but so we integrating back in time for 160 years because we know the chemical age, the estimate of the age of the cluster, and we just want to check if the moment of maximum density would correspond to the age of the cluster from other techniques to find it. Am I answering your question?
Which integration scheme? What algorithm?
I'm sorry. Yes, so we used Gadget 4, and this is just in-body simulation and body integration with direct summation.
Was it just a leapfrog?
In external potential.
So probably a leapfrog? Leapfrog. Yeah.
Maybe.
Gadget 2.
Yeah, I don't know whether it's sure.
Yeah.
But we have reached our 5 minutes of questions. I think. All right, Heidi, if you have a quick one, go ahead.
I just wanted to ask where in the orbit the stars are now, because I was wondering if that could somehow. I'm thinking about your density going down as you go backwards, and I was wondering if there was a way that because you were at Apogalacticon or something that you would be it could possibly explain that. Anyway, and I also want to say that's great work for 4 weeks.
Thank you. If I understood the question. So the orbit of the stream is almost circular, and we also try to set it on the circular orbit and see if it will change the density. Yes, because we would expect the changes in density correlation with pericenter and epicenter of the orbit. Yeah, but this peak is not related to pericenter or epicenter.